Welcome to this explainer. Okay, let's just dive right into it. If you're an IT professional looking to level up to a senior engineering role, or maybe you're aiming to land that high-paying job at a big tech company, there is one major, undeniable hurdle you've got to clear: the system design interview. So today, we're breaking down a high-yield study guide. We're going to cover the 30 fundamental building blocks you absolutely must know to architect real-world applications. And don't worry, we're going to make these complex topics incredibly accessible.
Right off the bat, this is the classic question, isn't it? How do you scale a system from just one single user to 1 million? Every application starts small, but what actually happens when it goes global? Throughout this explainer, we're going to trace the exact evolution of a basic app as it transforms into a massive, globally distributed system.
Here's our roadmap for the journey. We'll start with the core architecture basics, move into storing and managing data, and then tackle scaling for high traffic. From there, we'll explore optimizing database performance, dive into real-time and microservices, and finally wrap the whole thing up with security and API management. I promise you, we're going to build this architecture logically, step by step.
So let's start right at the foundation with Section 1, the core architecture basics. We need to know how devices actually talk to each other across the internet.
Pretty much every web app out there relies on a client-server architecture. The client, say your mobile phone, needs to find a server. But computers use IP addresses, which are kind of like phone numbers. And since we humans much prefer typing out easy, catchy names instead of stringing together a bunch of random numbers, we use the Domain Name System, or DNS. DNS is literally the internet's phone book. It maps a human-friendly domain name to a machine-readable IP address. Now, once they actually connect, geography becomes a huge deal. If a user in India sends a request to a server in New York, that physical distance creates a round-trip delay, which we call latency. To fix this, we might use proxy servers to route traffic more efficiently, or just deploy our application across multiple data centers worldwide.
So once they're connected, how do the client and server actually exchange data? Well, they don't just throw raw HTTP text at each other, they use APIs. And the two heavyweights here are REST and GraphQL. REST is the absolute industry standard. It uses your standard HTTP methods like GET and POST, it's stateless, and it is super easy to cache. But it does have a flaw. It can overfetch data. You might ask for a user's name and accidentally get their entire life history back. To solve that exact problem, Facebook introduced GraphQL. With GraphQL, clients ask for exactly what they need in one single query. The trade-off, though, it requires way more server processing and is notoriously harder to cache than REST. Moving down the stack, we hit Section 2, storing and managing data. Because once your API actually receives that data, it has to live somewhere permanently. And this brings us to the biggest crossroads in database design: SQL versus NoSQL. Look, if you're building a banking system, you need SQL, period. It uses tables with a strict predefined schema and guarantees ACID properties, which means you get incredibly strong data consistency. But what if you're building a massive social media feed? That's where NoSQL really shines. It drops the fixed schema for extreme flexibility and high scalability, using models like key value or document stores. In modern complex systems, engineers actually frequently use both of these side by side depending on the specific job.
All right, so our data is safely stored. But what happens when our app suddenly goes viral? That brings us to Section 3, scaling for high traffic.
Picture this scenario. Your user base absolutely explodes overnight, and your single application server is choking under the weight of 1 million requests. It's crashing. What is your immediate solution?
Well, you generally have two choices. You could use vertical scaling, which is scaling up. This basically means buying a bigger, beefier server with more CPU and RAM. It's a quick fix, sure, but there's a hard hardware limit, it gets exponentially more expensive, and if that one mega server crashes, your whole app is dead. That's exactly why senior engineers almost always favor horizontal scaling, scaling out. Instead of one giant machine, you add multiple standard servers to share the load. It gives you nearly infinite capacity, and crucially, it is fault tolerant. If one server dies, the others just keep humming along without a hiccup.
But wait a second. If you have 10 servers now, how does the user know which one to talk to? Enter the load balancer. It sits directly in front of your back-end servers, acting as the ultimate traffic manager. To ensure absolutely no single server gets overwhelmed, it uses specific algorithms. It might use round robin, which passes requests sequentially down the line, or least connections, which actively finds the least busy server, or even IP hashing, which consistently routes a specific user to the exact same server every time.
Okay, so our application servers are scaled out beautifully.
But now all those servers are hammering our single database. Let's tackle Section 4, Optimizing Database Performance.
When your database inevitably slows down, here is your interview cheat sheet. First up, indexing. Think of it exactly like the index at the back of a textbook. It lets the database jump directly to the right row without scanning every single page. It speeds up reads massively, though it does slow down writes a bit. But if your read volume is just way too high, you turn to replication. You keep one primary database strictly for writing data, and you sync it to multiple read replicas. Now, if your data size gets too massive, we're talking terabytes of data, you use sharding. This horizontally partitions your data by rows across multiple servers based on a key, like a user ID. And finally, if your tables just have too many columns slowing things down, you use vertical partitioning to split those tables by frequently accessed columns.
Now, because reading from a spinning hard disk is always going to be a bottleneck, we need a faster solution. Enter caching, storing frequently accessed data directly in lightning-fast memory. The standard approach here is the cache-aside pattern. It goes like this. Step 1. The app checks the memory cache. Step 2. If the data is there, boom, instant return. Step 3. If it's not, the app fetches it from the slower database, saves a copy in the cache with a time-to-live expiration, and then gives it to the user. Next time they ask for it, it's instant.
Now, as our data spreads across multiple servers and regions, we hit a fundamental, unbreakable law of distributed systems, the CAP theorem. It states you can only guarantee 2 out of 3 things: consistency, availability, and partition tolerance. Because network failures, or partitions, are just inevitable in the real world, you always have to have partition tolerance. There's no getting around it. So, the ultimate engineering trade-off is choosing between consistency, meaning everyone sees the exact same data at the exact same time, and availability, meaning the system never goes down, even if the data a user sees is slightly out of gate.
And that brings us to Section 5, Real-Time and Microservices. How do we make this massive system feel fast, modern, and perfectly coordinated?
Normal HTTP requests require the client to constantly ask the server, hey, any new updates? That's called polling. And honestly, it's a huge waste of bandwidth for things like live chat or real-time stock dashboards. The fix? WebSockets. WebSockets create a continuous, persistent two-way connection between the client and server, allowing the server to push updates the millisecond they happen. But what if a server just needs to talk to another server, like a payment gateway telling your app a transaction cleared? For that, we use webhooks. Instead of polling, the payment server just fires a single instant HTTP post request to your server exactly when the event occurs. It's incredibly efficient.
You know, at this scale, a single monolithic codebase becomes a total nightmare to manage. So we break it down into microservices, small, independent services that have their own databases. To stop these services from blocking each other while they're communicating, we decouple them using message queues for asynchronous processing. Meanwhile, from massive unstructured files, like user video uploads, we drop those into highly scalable cloud buckets called blob storage, like Amazon S3. And finally, to deliver assets globally without buffering, say for a user in India trying to load an image hosted in California, we use a CDN, a content delivery network. This caches static files on servers right in the user's geographic backyard.
Wow, we have built an absolute beast of a system. Now, let's wrap it all up with Section 6, Security and API Management, to keep this whole thing safe and functional.
So the absolutely crucial point here is that all this scalability we just built means absolutely nothing if a malicious bot can just spam your servers into the ground. That's why we implement rate limiting. It assigns a strict quota, say 100 requests per minute, to a specific IP address or user. If they exceed it, the server temporarily blocks them, preserving those precious resources for your legitimate users.
But where do we actually put this rate limiter? You definitely don't want to build it into every single microservice. Instead, you put an API gateway right at the front door. It acts as the single entry point for all client requests. It handles centralized authentication, enforces that rate limiting we just talked about, and then routes the sanitized, approved request to the correct internal microservices. It is your system's ultimate bouncer and traffic cop rolled into one.
Finally, there's one last safety net we need to talk about: idempotency. Imagine a user's internet connection stutters, so they furiously hit refresh on a checkout page. Your system might actually receive 3 identical payment requests. Idempotency guarantees that doing an operation multiple times produces the exact same result as doing it just once. By assigning a unique ID to the initial request, the system can simply check if that ID was already processed. If yes, it safely ignores the duplicates, which means no accidental double charges.
And there you have it, from a simple client-server ping all the way to a load-balanced, microservice-driven, globally cached architecture. Mastering system design isn't just about memorizing lines of code. It's about deeply understanding the core trade-offs between consistency, availability, and scale. So I want to leave you with this provocative thought. Armed with these 30 concepts, what incredible scale will your next system design achieve? Keep learning, keep building, and good luck out there on those interviews.